The goal of this experiment is to generate non-Gaussian states of traveling optical fields with high fidelity, including single-photon and coherent state superpositions known as Schrödinger cat states. This is achieved by using non-classical correlated beams as a primary light source. As a second step, a single photon is detected on one beam, which results in projecting the other beam in a heralded conditional quantum state. This is known as the conditional preparation technique, where an initial Gaussian resource is combined with a non-Gaussian measurement such as photon counting. Next, the heralded state is measured by homodyne detection in order to perform the full quantum state tomography. Ultimately, results are obtained that show high-fidelity quantum state engineering based on two different optical parametric oscillators.
The presented technique enables the generation of quantum states that are important resources for a variety of information protocols. Significantly, our procedure based on optical parametric oscillator, or OPO, makes possible to obtain a very low admixture of vacuum, high-fidelity states, and the emission into a well-controlled spatiotemporal mode thanks to the OPO cavity. This feature facilitates the use of these states in subsequent protocols, where they may need to interfere with other optical resources, for instance in optical gate implementations or in more complex quantum set engineering.
To perform this procedure, build a semi-monolithic linear cavity for improved mechanical stability and reduced intracavity losses. Include a KTP crystal and an input mirror that is directly coated on one face of the nonlinear crystal.